Hello, everybody. Welcome to Mankind in Training. Sorry I've been away for so long. I've been quite busy. Got some jobs we picked up, and I just haven't had the time. But I had a request to do a C++ deep dive, and I'm going to do that right after this video, like this evening even. So, but first things first, I was showing some things I was doing at my other job from my other job to those people, what you would call, I don't know, lay people, I guess. And they, just about everyone that looked at it was like, they took a look and went, whoa, threw their hands up and just was out of the building. And I just don't I'm gonna try to demonstrate some of maybe these hang-ups of things that people see in mathematics and go, whoa, yeah, I'm out. And I think part of it, big part of it, is Greek letters and their usage and the fact that they get used for different things at different times by different people uh, about different things. Anyway, we'll get into this. I'm going to go over to the paint, or actually, I think they have a thing right in here. Yeah, we'll do that. We'll do the whiteboard for now, and I'll do a different video after this regarding. All right, sorry if this takes forever. So first things first, I'm going to go over um the Greek letters. Firstly, you'll see these two paired together. They're alpha and beta, just like that. They're very frequently used. You'll see them a lot. Another one that you will see is mu and nu. Those are going to be frequently used. You'll usually see something like this, the letter G, and then there will be a sub mu nu. Be a sub mu nu like that. You'll see that. That's another thing maybe I should explain. You'll see sub notation, like A. A is complicated, so we broke A up into a set that is A naught plus A 1 plus A sub 1 plus A sub 2 plus dot 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 plus A sub n, and then n to the set, like that. We broke A up into littler pieces. You'll see notation like that. In this case, this is a coupled pairing. G mu nu itself is an entire, like, you should think of that as an entity of its own, even though it's made up of several characters. So let's get to some more Greek letters that I should be flowing along with these a little faster, maybe. Big one that you're gonna see a lot is sigma. That's another one that people see and they're like, "Yep, I'm out of here." Sigma just means a summation. It means you're going to add all of the elements that are after this. There's usually a counter. The counter is usually I or X or N something. I equals 0 is a starting point. And we want to go I equals 0 all the way up to 10, which means you're going to do this 10 times. And so take x sub I w sub I, and then we're going to multiply that by omega, which is this curly w like that, omega squared, and you're going to do that 10 times for the initial I that's coming in over here. I is an entity by itself, and you're going to sum it 10 times, so that plus the next one, I equals 1. Next, I equals 2. Next, so on and so forth. That's how those summations work. Another thing you'll see is a big pie. Not a delicious pie that's filled with strawberry rhubarb filling or whatever, but pie like this pie that you're used to seeing. This is the big pi, capital Pi, and this is a product. This is the same type of deal. There will be a counter. This time I'm using j. J equals 1. We're going to go from j equals 1 to the value of pi. And it's incremented. Let's do pi r squared, actually. And we'll do something like y e I. It should have been a negative I, sorry. H bar. So that's psi L over square root 2 psi. Psi usually represents the wave function, and that gets broken up into all kinds of different ways using various different methods. The wave function represents everything. Every second of your life is the wave function that you're entrapped in. We're all entangled together in a singular wave function, according to me. There's different ways to think about that, especially when it comes to measuring things, because things collapse. But I should probably get on with it. I'm taking. So next, quick calculus. This is another thing people see, and they're like, I don't know what that means. So you'll see things like this curly D. X over the curly D. And what this means is the partial derivative of x with respect to t, which is usually time. But sometimes it can mean if it's a capital T, it can mean a toroidal field. One of the things is context is key. Statistics things mean different things than physics things mean different things than number theory, set theory, type theory. There's so much mathematics, it'll blow your mind. But I'm determined to be knowledgeable in all these areas, and I want to teach you guys too. So I don't have a room full of people that. It'd be more impressive if I could actually sit down and explain all of this to everybody, and they sat and listened and learned something, rather than they were just looked at it and we were like, yeah, yeah, no, I'm not doing that. Anyway, the partial derivative of x with respect to time. What we're gonna do here to explain things like this, I'm also gonna take the partial derivative of y, also against the partial derivative of time. And I won't take a second just for the purpose of this demonstration. I'm gonna make a graph here with this being the y and this being the x. And then you have to do it again with one of the axes being time, or you make a three-dimensional one and then use the slices as time. Anyway, I'm gonna make it simple. We're gonna keep it two-dimensional. We're gonna include the time at a later time. So from the origin point, I have a steady climb, and then I drop. And then it seems like I'm in a slowly processive drop. And then it breaks again wildly, and then drops off completely. This is the end of the function, and this is the origin of the function. And we're going to call this, it went, yeah, that was 0. So we're going to do 1. It's going to be 2, 3, 4. So this function has a limit of 4 on the x, and it had a limit of, let me count up, maybe 1, 2. We'll call that 3 for now. 2, 1. So what we want to do here is find the area underneath of this line. This is a function. This whole line is a function, and it involves some sines and cosines, and then a whole bunch of wobbly woo. It goes pretty crazy here at the end. I want to find the area underneath of it. The typical technique that they do is they take a d, a derivative, a partial derivative. With respect to time, I'm going to show you what that means after we're done with this example. But so I'm going to take chunks. Sorry, that's not very straight. We're going to take some chunks. Anyway, you get the picture. This right here, one of these chunks, one of these squares, all the way up under the curve is a D. It's actually a normal D, and I'll explain why we turned it into a partial D here in a minute. And we take all of these we find out what D is. We make an approximation of what D is by drawing a rectangle, because we can find the area of a rectangle quite easily, and there will be these little tips that didn't get processed or whatever, but we'll find the areas of the rectangles underneath and make an approximation. Sometimes they'll right in this case right here, there would be a little bit of an overlap on the histogram. But then in some cases it undercuts it, like it would only go out like that. There'll be a histogram at the end that we measure all of the D's with. And then so the reason I picked a partial D in this example is just because people see the curly D and they don't understand what it is. But if people see a D, they at least may think that it's okay, it's a variable called D. Maybe it's dimension or something. At least gets you thinking. People see this curly D over, I don't want to do it. I'll explain it. It's not really too hard. These are essentially, each one of these is a derivative x with respect to, well, time in this case, and then if we wanted derivatives with respect to y, we'd have to take them similarly, but they would go like that. Anyway, so we would have a small approximation that came out to find them. Ah! Why can't I draw a straight line for the life of me? Wow, they all go curling up for some reason. There we go. Anyway, and then there, at least for two parallel lines. Oh my goodness. And then we would find the area in between there for dy. Say this function is three-dimensional. Now we have I'm going to add a new axis to this graph that goes out here, and this is time. Now this function, this is peak actually, and then it has a mirror side. So think about that as the limit now over here is, we'll call that 3 as well on the t line. That's the limit to the function. And then you would take slices the long way down the roller coaster like this, parallel with the two lines as a D. And sorry, this is, I know, probably boring and maybe unnecessary because there's a lot of other people that might explain it better. Nextly, integrals, integral calculus. So you took all these derivatives. A derivative is a portion of a large function, and now you want to put them all back together. The integral is the antiderivative. It is putting everything back together. So when you see a long, goofy thing like this with the I equals 1 or 0 underneath of it, and it goes all the way to infinity or something crazy, that is integrating the in this case, it should be integrating to time, not anyway, and then you'd be integrating x and y, d, d, followed by whatever this function actually the line that we came up with initially for the starting point of this function before it was projected out over time. And it could be whatever, I'm not it'll involve some sines and some cosines and yeah, that sort of stuff. Let me grab you some more magic eraser. Here are all the drawings. All right, so we had alpha, we have beta, we have sigma. I did that upside down and backwards. Sigma also has a counterpart that is used like this, and that is used in statistics. Both of these are usually as the population and then a subpopulation or vice versa. We had mu. We had nu. Sorry, that looks a little bit like it'll have a sharper look. Disregard this goofiness here. It look more like that. There's another Greek letter that looks suspiciously like it's Upsilon, I think. Upsilon looks suspiciously like nu. Do not confuse them. Upsilon has got a little bit more of a curly. I do that. You'll see the difference if you look at them. There is I'm trying to get the important one. So now gamma. You'll see gamma a lot. Gamma also has the little gamma that looks like that. Gamma is important. There is epsilon. If people see this and they don't know what to do with it, they're like, I don't know what that is. Sometimes epsilon is just used to say in the this and that. and the epsilon symbol is literally in. It's this in that. There's this alpha x component in the set, or this is a vector or an array or something, this other part, and we're going to say this is in this. Or you'll see this isn't that was a Greek letter. This is not. This is just something that you're going to see. This usually denotes that something is in the real number set. That is all. You're going to see a lot of negative I that just there'd be 3 minus I, something that just means you're turning something into a complex number most of the time. E is just a transcendental number. It's similar to pi, but it's a little bit more than pi. Or no, it's less than pi. It's 2 point something, and pi is 3 point something. 3.1415, yada 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 yada. The other one's 2.7 something or other. E is the natural logarithms. That's another thing you're gonna see. There'll be log and then something or other inside of those brackets. A logarithm takes it and breaks it down by e, the natural log of something. So it usually counters anything that's been exponentially raised. So there's like e to the y, e to the y pi, call it. And e to the y pi, if you log e to the y pi, you'll just get log y pi, or you'll just get y pi. Let me continue on with these before I get completely lost. There is chi. It's a really goofy X. There is xi, spelled XI, and it looks a little something like that. There is, I'm gonna slaughter this, so don't laugh at me. There is zeta. There's that's supposed to be zeta. I'm terrible at drawing zeta. Um, uh, um, iota, iota, or it's got these are even less pronounced. They're shorter. Kappa, Magic K. Ooh. Omega. Omega, you're gonna see a lot of omega, and I don't know why I didn't draw that earlier. That's capital omega, and that's little omega. Maybe I should be writing the names underneath of them. Alpha, beta, these are the sigmas. Mu, nu, gammas. Epsilon, there's another epsilon. It just looks like a big E. R, this is chi. That's xi, xi. That's it's a facsimile of zeta. It's a it's a zeta cover band. Iota, kappa, omega, omega. There's more. I need to think of them. Oh, you're gonna see a lot of this. That is phi, phi, fo, fum. Just kidding. It's spelled PHI, phi. And then its capital is this. Phi. And then this is super duper important in physics. Whoa. Crooked. My line went crooked. Man, we weren't supposed to connect like that, and that's I don't know. These are the size, capital, okay, short and capital, phi, psi. What else are we missing here? So yeah, we explained that if I had x to the n and I did a logarithm of that, it would it would bring you n down into your normal plane space. Sorry guys, I'm trying to think of other Greek letters that I'm missing. There's probably like some doozies that are like, oh, what am I doing? There was Omicron, it just is an O and another O. These like lesser ones, you miss them. Pi, yeah, everybody knows pi. Eta, that, eta. Um, Theta. Wow, how did I forget theta? That's a rugged job of doing the capital theta, but that's what that one looks like. Um, oh, let me go. Angular frequency, omega. Theta is a measure of difference angle, usually. Psi is the wave function. Phi is like real particulate things. The real valuable measurable portions of things that you find in the wave function. They use mu and sigma and gamma for particle physics. Like some of the symbols like literally denote particles. You'll see that. Um, yeah, what else should I teach you before I go head first into trying to teach you some other things in Senpai and how to actually solve them? So I got rid of the Greek letter portion. So now let's get to some of the mathematical stuff. Things like you hear a vector, and a vector is a set of values. Not x1, x2, and dots here. Yeah. All right. That is a vector. Probably the vector, we'll call that uh, equals. That's the vector x. Now there are arrays that are just a set. I'm gonna cut this here. And cut that there. This is an array. So basically a column is a vector and an array is a row. sort of. They're arranged in that direction anyway. And then a matrix. So I want the matrix A. I want the matrix A to be 0, 1, 0, 1. And then I will continue to go. And 1. 1, x 0, -1, 1, 0, -1 x. Anyway, you get the gist. X -1, 0, x 1, -1, 0, x -1. So this is a matrix, a series of columns, rows of different values of different things. If this was, if I turn that into x naught and then turn that into x2, it could be a series of, people get creative with what you can do with matrices, how to multiply them, how to add them together, and sometimes it shortens the length of complexity, like time complexity, on things if you do matrix multiplication rather than a bunch of individual operations. If you can concatenate other things that it does quickly into a single thing, it actually shortens the total length of time it takes to do that task. I've been rambling for quite a while now. I'm not going to get onto bra and ket notation and the Dirac notation for the Schrodinger equation or anything, but this was a good little summary of some things that I'm probably missing some Greek letters here that I shouldn't be. I just these are the ones that came to mind when I did this quick. This probably wasn't all that quick. It's actually probably really long. Thank you guys for watching, and I will see you in the next video that I'm making in like 8 seconds of C++. I was supposed to do this for a long time. So I'll see you over there. Thank you for watching. If you enjoyed, subscribe, and thank you.